Okay, hi everyone. So third lesson I'm filming today. This one's going to be on Coulomb's law. These lessons kind of take a toll filming them. So yeah, luckily this one's short and won't kill me. So last lesson we looked at stuff to do with electric fields, electric field lines, the configuration that you can get when you've got a positive and negative charge or two positives or that kind of stuff. The parallel plate capacitors as well, the electric field strength between those. So what we're doing today is stuff to do with if you've got a charge, what is going to be the electric field strength of the field produced by that charge. If you have two charged objects, what is going to be the electric force between those two objects. So I should surely learn how to set this up in a way that doesn't require me to move as much. Anyway, Coulomb's law tells us the force between two charges Q1 and Q2 when they are separated by a distance of r. So this is analogous to what we were doing when we did gravitational forces. We had mass 1 and mass 2, and they were separated by a distance of r, and our equation was F equals G m1 m2 over r squared. This is just a analogous thing to that. Instead of having a value of big G, the gravitational constant, we've got a value of K, 9 times 10 to the 9 Newton meters squared per Coulomb squared. If you look at your textbook, there's going to be the equation, and it's going to be written out, rather than having a value of K, it's going to have a value of 1 over 4 pi epsilon naught. Epsilon is, I think, the permittivity of free space, something like that. Might be permeability. As part of doing these calculations, that doesn't really matter, because if you do 1 divided by 4 pi epsilon naught, that comes out to some constant value, which is 9 times 10 to the 9. So rather than calculate that every time you need to do a calculation, you can just say, well, whatever's out the front in your textbook is going to be this value, and you can use this when you do your calculations, save you some time, save introducing ways that your calculations could go wrong. So got this value of K, you've got the value of the charge of the first object, charge of the second one, the distance between their two centers. Normally when we're thinking about charged objects, we're talking about things like protons and electrons, where they are very small and the distances between them are much larger than that. So when we did gravitational field strength or gravitational forces, we were often concerned about, well, how far are the centers of these two objects from each other? We needed to account for that. Normally you don't need to do that for electric force calculations because of the small sizes of the objects that you're considering, but you might have to for some questions now and then if you've got big charged balloons, like they've been, you know how you charge a balloon, and there's a force between those. You might have to consider that when you do a question like that, but generally you won't. So an example would be, what is the force between a proton and an electron? It's got those two charges there, like I said last time. Charge of a proton, 1.6 times 10 to the negative 19 coulombs. Charge of an electron is exactly the same, except it's negative if they are 10 to the minus 8 meters apart. So this is a simple plug and chug question, where you just take your equation, plug in the numbers, chug through the calculation, and get out your answer. We've got a value of K. We've got the charge of a proton, charge of an electron, distance between them. Make sure that's squared. Make sure you've got brackets around that denominator so that you don't have minus 10 and then the 2 and you've got 102, or you don't have minus 10 squared and so you've got 10 to the minus 100 or something like that. Please make sure you've got brackets on there. Up the top, I've got brackets on here and I've got brackets on there as well. And if I took out all these brackets from there and there and there, I'd get exactly the same answer. They're not needed when I'm doing my BODMAS. But I always like to put brackets around these kinds of things because it's a bit of insurance. It makes sure that if you've stuffed up somewhere, that the calculation it'll probably say syntax error if you've stuffed up doing it this way because you've put in some symbol wrong. But without the brackets, it's easy to put something in, get out an answer, and you can't recognize that you've made a mistake because your calculator doesn't tell you, which it would have if you'd put in brackets and separated things out like that. So this is just a good practice. I'll put my brackets around those. I'd recommend doing it, but don't feel obliged to, because if there weren't brackets on these, you'd get out the exact same answer, 2.304 times 10 to the minus 8 newtons. So that's a fairly basic type of question where It's just two charges, what's the force between them? If you know the value of K in the equation and the distance between them, then it's very, very simple to do, assuming that you don't stuff up on your calculations down the bottom. And the only other thing that forms part of today's lesson is on electric field strength. Now, we've looked at electric field strength, we looked at the electric field strength between two plates, and we said that there was a uniform electric field between them. The field strength was the same at any point between those two plates. When we're talking about a charged object, say a proton, which I think is what the first example is. No, it's not. It's just about a generic object. If we were talking about a proton though, you know what its electric field looks like. It's those radial pointed lines that point away from the object. And when we're talking about the electric field strength of an object like that, the electric field strength is going to be strongest close to the object, and it's going to get weaker as it gets further away. Exactly the same as how a gravitational fields worked, how those got weaker as you got further away from the object producing the gravity. So electric fields work exactly the same. We've got that on R squared, the inverse squared law for electric fields, which means that if you double your distance from a charged object, your electric field strength is going to go down by a factor of 4 rather than 2 because of the squared. But I'm getting ahead of myself. So anyway, electric field. Last lesson, or a couple lessons ago, actually, I'm losing track of things. I said that electric field is electric force divided by the charge of an object, and we had that equation. That was good. The force on an object just from before is going to be Q over R squared. Now, as part of doing this, I've changed my notation. Rather than saying Q1 and Q2, I've decided to use the notation of big Q is the object producing an electric field. Little q is some other object that is having a force exerted on it by that electric field. So this could be my proton producing its electric field. I stick another proton out there. The big Q is the one producing the electric fields. The little q is the one that is experiencing a force because of that electric field. The reason I did that is that it becomes a bit analogous to gravitational fields. When we talk about gravitational field strength, we talk about big M up the top of this equation. We'd have Gm over R squared, and the big M would represent the mass of the object producing the gravitational field. So I like to be consistent with that and use a big Q to represent the charge of the object producing the electric field. Anyway, we divide that by the Q, the little q, the value of the object that's experiencing the force on it, and we just get out this equation for electric field strength, Kq over R squared. Exactly the same as the equation for gravitational field strength, like I was just saying, except instead of G you've got K, and instead of the mass you've got the charge, still divided by R squared. So an example of this, the basic one, an object with a charge of 6 coulombs, what would the electric field strength be 10 meters away from it? I was taking my numbers, my value for K, my value for Q, and my R squared. I put that in and I get out a colossally large value for the electric field strength. The reason for that would be that 6 coulomb is a lot of charge, like just a colossal amount of charge. So that's why that answer comes out to be so large. Yeah, normally you wouldn't get charges that large. You'd get charges on the order of the nano or the micro if you get into very big charges. But normally they are very, very small numbers, and this is one of those areas where it's good to know what your prefixes for units are. It's good to know that nanos -9, micros -6, millis -3. Those things are all on the formula sheet that you get on your exam, but you're going to need to practice using those. So if you're a bit confused about which one's which, you can either just go to Google and look up what is nano to get an answer, or you could just get a bit of practice in, download a previous year's physics exam, go to the very bottom of the summary sheet, see what's on there, see the little table where it has the prefixes and what they signify. I'd actually recommend doing that. Get some experience in using the summary sheet so that you're more familiar with what's provided to you, the formula sheet. I mean, when you do your exam, it's always good to know exactly what's on there before you go into the exam. So anyway, that's the electric field strength stuff. What you're doing is, I think from 2.2, again, I'll update that if I'm incorrect. but you can check it yourself. It's on the Fields question plan list. So anyway, you should just be getting on with those, doing the Ed Rollo questions that are corresponding to this stuff. Not much to talk about today.